So next set of reaction is addition of alcohols. I told it's a very important reaction. So carbonyl compound give addition reactions. So this addition reaction with alcohols to give the corresponding product, which depends on the catalyst. If it's acid catalyst or base catalyst, you get different products. So let's see what are the reactions are. So let me first deal with base catalyst. So in base catalyst, one equivalent of alcohol, I am representing alcohol by ROH, needn't be, okay? It reacts with one equivalent of the carbonyl compound. One equivalent of alcohol reacts with one equivalent of carbonyl compound. That is the first thing. Second thing, hemiacetal or hemiketal is the product, depending upon whether it's a aldehyde or a ketone. For ketone, ketones are the product. For aldehyde, acetals are the product. And the third thing is this is a reversible reaction. Okay, so let me see the reaction. How is it? So this is an aldehyde in presence of CH3OH, which is an alcohol. In presence of base catalyst, you get RCOH, H, OCH3. Okay, what happened? Base removes this H, removes this hydrogen. So CH3O minus, this goes and attacks here. So you get OCH3. Now a compound is called hemiacetal if it's a derivative of aldehyde. If a compound contains OH and OCH3 on the same carbon, it's called a hemiacetal or a hemiketal. Suppose instead of H, if I have a R dash, then here an R dash should be there, then it would be called a hemiketal. So if OH and OCH3 or OH and OR, let me write it as OR double dash so that to avoid confusion. So if OH and OR double dash or OR group and OH group are present on the same carbon atom, then it's called hemiacetal or a hemiketal. Okay. So these hemiacetals and hemiketals are generally unstable, so you cannot isolate them. Okay. Since hemiacetals and hemiketals are highly unstable, it's very difficult to isolate them. These hemiacetals or hemiketals, they become stable by forming cyclic compounds when the both carbonyl group and the attacking alcohol is present in the same compound. For example, let's take this compound CH2 OH, CH2, CH2, C double bond O, R. What happens? This rearranges, this alcohol gets attacks here to form removal of this hydrogen, so positive charge gone and that hydrogen gets attached here. So OH and O, this is the OR double prime group attached to the same carbon atom, you form a hemi. Here it's a ketone, so hemiketal. Okay, so that was about this. They are unstable, cannot be isolated. Here, in the case of acid catalyst, one equivalent of carbonyl compound reacts with two equivalents of the alcohol. That's the distinction, and the product is nothing but ketal or acetal, depending upon whether it's an aldehyde or a ketone. And third, the catalyst in most cases used is para-toluene sulfonic acid. Para-toluene sulfonic acid. Let's go about how it happens. H plus, rearrange this to this, OH plus, this resonance form. Okay, and now let my CH3OH, this alcohol attacks here, then you'll get I'm sorry, this is the resonance form. This OCH3 comes and attaches here. Okay, so H plus, acidic medium, RCOH twice, HOCH3, removal of the water molecule. Okay. I'm continuing it here. From this step, we have RCOH and OCH3 here picks a proton from the acidic solution, so you get RCOH twice H OCH3. Okay, then this gets a positive charge, removal of water molecule, and then you have RC plus H OCH3. And remember, this particular step is the crucial step or the slow step of the entire mechanism. And then here again you have the alcohol being added to COCH3 with a positive charge on the oxygen atom, and then this hydrogen gives a H pair of electron and leaves a proton. Finally you get RCOH3 OH3H. So when two OR groups, in this case OCH3 groups, are present on the same carbon atom, it's a ketal or acetal depending upon your substrate is an aldehyde or ketone. If it's an aldehyde, you get an acetal, in this case it's acetal, whereas if you get a ketone, that is, suppose if I replace this H by R, then you will get a ketal. Remember, that is the slow step. And one thing that you should be know that all the above steps are reversible. Okay, all the above steps are reversible. So what, though I have not kept the arrow, so you can see that all the steps are reversible, and this is the resonance form. Okay. Now the crucial step is basically removal of water molecule. So this is still here is nothing but this is a hemiacetal or hemiketal depending upon the substrate. Now the removal of the water molecule is the crucial step. So after formation of this hemiacetal, if this water molecule is removed from the solution, okay, or if as fast as you remove the water, the faster will be the rate of reaction, so far more will be the yield, because this is the crucial step. Okay. Now one more point to be noted is that formation of the acetal and ketal requires an acid catalyst, because to facilitate the removal of the water molecule in the fast step, and you should know that these are reversible, and if you keep on adding water molecule, it reverses back and gives rise to your aldehyde. However, one point should be noted that acetals and ketals are very stable in basic solution. That's why in basic solution you get only hemiacetals and ketals, but not all the way to acetals and ketals. Now how to get cyclic acetals and ketals? So you have a ketone and I am treating with a diol. So for cyclic acetals and cyclic ketals, you always require what you call is a diol, and then in the presence of acidic medium, again remember acid catalyst is required because you need a ketone, not a hemi one, and therefore you will get this. Okay. Now acetal and ketals are generally used as protective groups for protecting the carbonyl compound. So in a carbonyl compound, let's say it's a carbonyl compound R, and then again you have a ester group or alcohol group, whatever. If you want to protect this part from reacting, what you do, you make it react with an alcohol, and then in acidic medium, then you form acetal or ketal, and then due to the formation of the cyclic acetals and ketals, generally you prefer diols because you form a cyclic ketal or cyclic acetal. That's more helpful. If you use a single one, that is if you use a monoalcohol, maybe not so stable. Generally cyclic diols are used. So, diols are used to form this cyclic kinds of ketals or acetals. So this particular group is protected, and now whatever reaction you do in any medium, these groups will be affected while this group is particularly protected. And so if the reaction is taking place in the presence of strong bases, that is in strong basic medium, or you have a very strong nucleophile which is going to react, then this acts as a protective group. However, if it's an acidic medium, you know the reaction is always reversible, so you can get back the aldehyde and ketone. So it's not effective in acidic medium. However, if your main reaction of this compound is taking place in a basic medium and you want to protect the carbonyl group, then you treat it with a diol to form this cyclic ketal or acetal, and then after the interreaction is over, to the product you treat it with acidic solution so that you get back your original compound. So these are used as protecting groups. So I will be taking chemical properties due to the carbonyl group. Now, a quite important one, reaction of diazomethane, addition of diazomethane, in all this type of reactions, nitrogen is not retained in the product. Okay, now if you have aldehydes and you treat with diazomethane, you will get methyl ketones as the product. So I am taking an aldehyde RC=OH plus this is diazomethane, negative charge on carbon, positive charge on nitrogen. This goes and attacks here, so you will be having RCO, CH2 and triple bond N plus and O minus with an H. So now this oxygen tries to form a bond with the carbon. Okay, as this hydrogen goes to this, and this goes here. Okay, then you will get R C double bond O CH3 plus N2. I hope it's clear. This O minus comes here trying to form this double bond, causing this hydrogen to leave. This hydrogen goes to here. As it goes here, this bond shifts and leads to the addition of nitrogen gas. Okay, so this hydrogen shifts to this carbon. As a result, this bond cleaves and nitrogen gas is released. Now if you see, this is a methyl ketone because you have a methyl group in the ketone, and this methyl ketones give iodoform test. So if you have any compound and you treat it with an diazomethane and finally test it for iodoform test, and if it gives a positive iodoform test, that means you have an aldehyde in that compound, and that aldehyde forms a methyl ketone which gives rise to the iodoform test. If you take ketones react with diazomethane to form oxyrenes. So you have R C double bond O R prime, and this is diazomethane. Sorry, a minus charge here and a plus charge here. Let me write it R prime. Okay, I have already written that. What happens? This, if it tries to form a double bond here, there is nothing which can leave because alkyl groups cannot leave generally. So it goes and attacks this and leads to the cleavage of the nitrogen gas. So finally you get R C O attacks this CH2 R prime plus N2. What are oxidants? As studied in ether chapters, oxidants are cyclic ethers. So that was with aldehydes and ketones. Now what about cyclic ketones? So cyclic ketones, let me take an example. This is cyclic ketone. You have diazomethane, negative charge, positive charge on nitrogen because nitrogen cannot form 4 bonds generally. So you will get this kind of compound. Right? Because this goes and attacks on this carbonyl part, and okay, I'm sorry, that was wrong. It goes and attacks onto the carbonyl group. So O oxygen gets a negative charge, and this gets attached here. Now two things can happen. One thing is this here and this leaving, then you will get the product as the oxyrene. Okay, or even one more thing may happen, that this particular may cleave, okay, and you may have a ring expansion giving rise to a higher order ketone. So even normal straight chain ketones, also open chain ketones, can give a product of the next homologous series by this method. Okay, cyclic ketones give two products. One is the oxyrene, and is a ketone of a higher carbon atom, that is of the next homologous series. So that was reaction with diazomethane. Next we'll have reaction with ammonia. So reaction with ammonia. Reaction with ammonia, the product is unsubstituted. Unsubstituted imine is the product if you react with ammonia. Okay. The problem is the unsubstituted imines of aldehydes are so unstable that they polymerize to form different polymers. So first formaldehyde. Formaldehyde is HC double bond OH. If you treat with ammonia, you know the same kind of reaction at hydrazine, removal of water molecule. So H2O gets removed and carbon forms double bond with nitrogen of the ammonia. So plus water molecule. Now this particular thing polymerizes to form what is called as urotropin. Urotropin, or it's also called hexamethylene tetramine. Hexamethylene because 6-methyl group, tetramine 4 nitrogen. Now surprise how it's formed, but basically it's an unsaturated compound, that's a ring compound. Let me draw the structure of urotropin. That is hexamethylene tetramine. You have 4 nitrogen groups, so 4 ends. Just join each of them externally and then also join it internally with this being the methylene groups. So you have 6 of them. It's hexamethylene tetramine. If you have acetaldehyde, it forms aldimine, which is nothing but removal of water from ammonia from acetaldehyde. So CH3 CHNH, CH3CH double bond O would be the aldehyde. Removal of water molecule from this with ammonia, so you get aldimine, and this trimerizes to form a cyclic amine, which is nothing but is the cyclic amine, which is formed by trimerization with acetaldehyde. Whereas if you have a ketone, let's take acetone. Acetone with ammonia will form an adduct, which is an addition product, and when this adduct is further treated with the ketone, that is acetone, you will get diacetone ammonia. What happens? CH3 C double bond O, CH3 plus ammonia. Here it will form CH3COH, CH3 and H2. This is the addition product, and when you treat it with another acetone, this is acetone, then you get diacetone ammonia, that is CH3C. The structure is retained, whereas removal of the water molecule, and this is diacetone ammonia. So it's diacetone ammonia. Okay? Next reaction, addition with water. So if you have carbonyl compounds, and you add water to it, basically you get geminal dions as the product. Geminal dion means 2H group attached on the same carbon. You know water is a very pure nucleophile, so it is generally acid catalyst, and the reaction is always reversible. So you have I'll take a ketone plus water, presence of acid will form the gem diol. This is highly unstable. Okay, unstable gem diol. Now how do you stabilize a gem diol? First thing, gem diol is stabilized. It is stabilized by the presence of -I groups on the alpha carbon. If you have -I groups on the alpha carbon, then the gem diol is stabilized, and also if there is intramolecular hydrogen bonding, that is hydrogen bonding present within the same molecule, then the stability is increased. Whereas the stability is decreased if you have +I groups around the carbon atom. Okay? So, if there is steric hindrance because of the +I group, so if there is steric hindrance due to +I groups around the alpha carbon of the carbonyl group of the carbonyl compound, then the gem diol is not stabilized, whereas it's stabilized if it's exactly the opposite, that is -I groups present on the alpha carbon, and if there is intramolecular hydrogen bonding, that is hydrogen bonding in the same molecule. Let's see some examples. So if you see this is one more case where it's stable. This is highly strained because of sp2. It's trying to be planar, whereas this double bond O is not allowing it to be. It wants to be planar, whereas there is highly straining strain. So this tries to be stable if it stays as a diol, which is geminal. So this is stable in case of a geminal diol. And same thing as what occurs with, so that was the end of reaction with water. What occurs in the formation of thiols, that is addition of thiols. Instead of alcohols, if you add thiols, you will have, there you had 2 OR groups attached. Here in this case we will have 2 SR groups attached, and this is called Mozingo method. This is addition of thiols, and you can protect a particular carbonyl group using either formation of ketones as explained before, or you can also protect it by addition of thiols and again treat it back to get back the carbonyl compound. Okay, so thiols are also used as protecting groups. Now remember, because of the -I effect, decreasing -I effect of the S- thiols, thioketones and thioacetals are much more stable. So thioketones and thioacetals are much more stable than the normal ketones and normal acetal because of the decreasing -I effect of the S-. So you know C2H5OH, if you have OH, the -I effect is more, whereas for SH the -I effect is less. Sulfur has less -I effect, so therefore thioketones are more stable. So if you hydrolyze the thioketones, you will get back the carbonyl compounds. let me tell one more reaction. This is called Michael addition. This is a part of Michael addition, which is star-enamine synthesis. Remember, Grignard reagent reactions are already taught in the previous chapters. So, this is alpha beta unsaturated ketone, and you treat it with a base. This is just for your remembrance. Okay, so this is formed. You add alcohol to it. Let me call this as B. Then you tautomerize and then add water with acid. Then you will get okay. So to this you will get the cyclic ketone with this attached to the alpha position. This is your star-enamine synthesis or Michael addition, that to this particular compound you get particular compound, you form a cyclic ketone with its alpha position being attached by the original alpha beta unsaturated compound, with the unsaturated being lost. What is this? This is nothing but an enamine. Side point, addition of HCN. So if you add HCN to aldehydes or ketones, you will find cyanohydrins in the presence of a base. So cyanohydrin is this. So all aldehydes will form cyanohydrins. OH and CN on the same carbon is tetrahedral cyanohydrin. This is called cyanohydrin. All aldehydes will form cyanohydrins. Among ketone only acetone, butanone and pinacolone, as well as 3-pentanone. Only these ketones give rise to cyanohydrin test, whereas all aldehydes will give rise to cyanohydrins except formaldehyde. All other aldehydes give rise to a racemic mixture, and these cyanohydrins are used as a test for aldehydes and the specific ketones only, because of the racemic mixture that is formed in the solution. The another reaction is when bisulfide, sodium bisulfide or potassium bisulfide is treated with aldehydes and ketones. You get a white solid, and this is a test for again carbonyl compounds, and this white solid is easily converted back to the aldehyde or ketone by treating it with dilute HCl or alkali or even formaldehyde. So if you treat it with dilute HCl or alkali or even formaldehyde, this white solid is converted back into aldehydes and ketones. So basically this is used for purification of aldehydes and ketones from their original sources. Because if you treat an aldehyde and ketone with sodium bisulfate, you get the white solid, it precipitates out. Now again, if you treat it with dilute HCl, alkali or HCHO, that is formaldehyde, you get back a compound. What happens? This is the thing. You treat it with HSO3. This can be R or H. One of them should be R, obviously. Then you will get this bisulfite adduct, the white solid. Okay, if you are in acidic medium, this can also exist as in basic medium it will exist like this, in acidic medium it will exist like that. Okay, so this is also a test for carbonyl compounds. So that's basically the end of this chapter. I have not touched the condensation reactions, which can be as a part of other chapters or even taught separately. So other than condensation reaction, all the chemical properties have been covered.